Hi everyone. Excuse me for my voice. I'm a bit sick at the moment. So hello. In this video, we will be discussing our review for Test 3, which is on chapters 7, 8, and 10. So chapter 7 is on what are called confidence intervals. Remember, a confidence interval tells us a specific range of values that we're a certain percentage sure of that the actual population parameter lies within that range. So we're using a sample to try to figure out a parameter of the population. And, we can't be 100% accurate. So very often we're looking for a 90% confidence interval or some other sort of percentage. Because you can never be 100% sure of anything in statistics, essentially. And so this is very important. And there's a couple different ways to talk about confidence intervals. First, the first situation is when we know the standard deviation of the population, right? That's what sigma refers to. Remember, that's the population standard deviation. And so if we know the standard deviation of the population, we have one way of finding the confidence intervals for a mean, specifically for the mean of the population. That's what we're looking for in those. Similarly, we could be looking for the mean of the population when sigma is unknown. So we don't have the population standard deviation. We don't know sigma. So we essentially use our best guess of what sigma is, which is S, the standard deviation of the sample. And so we've got another formula when that's the case. And then we could also find confidence intervals for proportions. Remember, that's essentially binomial distribution because they're surveying somebody and they're saying yes or no to something. It boils down into a percentage being yes, a percentage being no, and then you put those in the formula. And then in section 7.4, we're looking for confidence intervals of variances and standard deviations. So let's briefly talk about these and the formulas involved and when to use them again. So here's the stuff for when sigma is known. That's the population standard deviation, sigma. So when we know sigma, and we're looking for the mean of the population, remember that's mu, we're trying to estimate mu as best we can, we use the formula x bar plus minus z star times sigma over square root of n. And there's a couple z stars that are used very often. 90% confidence interval is 1.65, a 95% confidence interval is 1.96, 99% confidence interval is 2.58. And for other confidence intervals, you've got to use the chart. Remember the Z table, but I'll probably talk about that here as well. And there are stipulations that, number one, the sample has to be random, and there needs to be some size requirement. So number two, either we have a sample of 30 or more, or if the sample isn't 30 or more, we know that the distribution is at least normal. Then we can still use the formulas. So we looked at some examples here. In this case, so you just essentially have to, they're basically word problems. It can be a bit tough, but there are certain keywords that you can digest in the problem to kind of clue you in on what formulas to use. So let's again go through this question. A researcher wishes to estimate the number of days it takes an automobile dealer to sell a Chevrolet Aveo. So he's trying to find the population average for a number of days that it takes to sell the car. So we know we're looking for mu so far. So we've already boiled it down into either 7.1 or 7.2. So now it says a random sample of 50 cars had a mean time on the dealer's lot of 54 days. And then it says assume the population standard deviation to be 6 days. So that's sigma. We can then identify that to be sigma. And so, of course, since we know sigma, we would use this formula that we just spoke of. X bar plus minus E star times sigma over square root of n. So you just identify all the materials, all the constants, I should say. N is 50, X bar is 54. Remember, N is the sample size. X bar is the mean of the sample. Sigma is the population standard deviation. And Z star represents the confidence interval that they're telling us. They said use the 95%, which is a Z star of 1.96. So I think it's really helpful to, write down all of your variables before even thinking about what the formula is. Because then when you have all them there, that kind of informs you which formula to use. Oh, I've got to use the formula that is N, X bar, sigma, Z star. So you know it's this one. Anyway. So we plug in all the stuff. We get our lower and upper bounds. So we're essentially 95% sure that the actual mean of the population is between 52.337 and 55.663. And another really helpful thing is to always draw a picture for these confidence interval questions so that you, it just helps to crystallize what's going on in the problem a lot better than if you didn't have it. So we saw another example here. It was a 99%, which we know to be 2.58. And I put here how to find Z star. So yeah, the next one's 98. We don't know that one from here. We memorize, you don't have to memorize any of them, I guess. You could always just use the chart. That's fine. So to find Z star, a confidence interval is the middle, whatever percent that it says. So if we're looking for a 90% confidence interval, we draw the picture, and the inside must be 90%. And since it's a normal distribution, it's symmetric. So therefore, we know that there's, since 10% remaining, we've got to distribute that 10% to each tail, essentially, the left tail and the right tail. So they must have 5% data in there of the data. And then I just use the one on the left, and then the one on the right is just the positive of the one on the left, again, due to symmetry. Right? Anything to the left of the middle is 0. Anything to the left of 0 is negative. Anything to the right of 0 is positive. And so if each tail is 5%, that means this boundary on the left should have 5% of the data to the left of it, aka 0.05. So we can look for the Z value representing an area to the left of it being closest to 0.05, which is this one right here, negative 2.58. So this one had a weird confidence interval, 98%. So again, we draw the picture. And if we want a 98% confidence interval, that means the middle needs to be 98%. We've got 2% left, so we've got to distribute it evenly amongst each tail, leaving 1% in each tail. So to find that left boundary, we look for the z value with an area to the left of it being closest to 0.01. And the one closest to 0.01 is this 0.0099, which is a z value of negative 2.33. So that would be our z star is positive 2.33. Remember, z star is always the positive version. I guess it doesn't technically matter. When you plug it in the formula, you get plus minus anyway, so. But, yeah. That's how to find z star for confidence intervals other than 90%, 95%, and 99%. So here's the formula for the minimum number of sample size necessary to make as accurate of a specific of an answer. And remember, you always got to round up for this one. Even if you get like 70.1, you would round it up to 71. Okay, and hope that's good for 7.1. 7.2, this is when we don't know the population standard deviation. So we use our best guess, which is the sample standard deviation, S. And additionally, we also don't use the Z tables. We use the T tables for this one. We use T star instead of Z star, and sigma is replaced by S in the formula. So the formulas are identical. It's just instead of Z star, it's T star. Instead of sigma, it's S. And those same stipulations need to hold. So here we looked at an example, and it does say there in the blue, the standard deviation of the sample temperatures was 8 degrees. So that's the key word there. It says the sample standard deviation, or the standard deviation of the sample. That's S, not sigma. Sigma would be the standard deviation of the population. Okay, so we know we've got, when we go through it, we get our N, our X bar, we get an S, and it's a 95% confidence interval. So what we do is we come to the chart, and remember the degrees of freedom is N minus 1, which in this case would be 11. So you look up the row of which degrees of freedom you're in, and then since we're doing a two-tail test here, we use that the bottom row that says two tails. Right, because the tails represent 5% of the data. 95% is the middle, so we've got 5% left for the tails. It's a two-tail test. There's 5% of the data left. That's 0.05. So we line it up with the, I guess I can just color this in here. I probably should have done it when I did the lesson. This one right here. Or I guess I don't want you to use this this part. The top rows are better. So a good example there. And here we have another one. It's a 95% confidence interval. It's a sample of 8 adults. That's our N. They had an average weight of 12,300. That's our X bar. A standard deviation of the sample, keyword of the sample, was 22 pounds. That's our S. And it's a 95% confidence interval. So again, we got everything. We need to get our T star. Our degrees of freedom is going to be 7, and it's a two-tailed test. And we've got 5% of the data left in the tail. So it's that same column, actually, as the last one. So we get 2.365 for our T star. Plop it all in the formula, and we're good to go. So that's 7.1 and 7.2. It's about estimating the mean of the population with some level of confidence, either when we know the population standard deviation or we don't know the population standard deviation. And you've got to really pay attention to that key word there when it's talking about standard deviation. It will say either the population standard deviation or the sample standard deviation, and that keys you in on which formula to use, either the x bar plus minus z star times sigma over square root n, or the x bar plus minus t star times s over square root n. Okay, and so we could also look at confidence interval for proportions. And that's when we're looking for the population proportion. We take some sample, and according to that sample, we make extrapolations about what we think would happen in the population. And we get a very similar formula. It's called p hat plus minus z star times the square root of p hat q hat over n. Again, remember, p hat is the sample proportion. Q hat is 1 minus p hat because they're complements of each other, right? If 43% say yes, 57% say no. It's just always going to be that way. And p hat is the number of people that say yes over the total number of respondents, essentially, if it doesn't just give you the percentage. So here in this, let's look at this one. A survey conducted by Sallie Mae and Gallup of 1,404 respondents found that 323 students paid for further education by by student loans. Find the 90% confidence interval of the true proportion of students who paid for their education by student loans. So they take the sample to try to make guesses about the whole population of the country, for example. And so we get our p hat. That's going to be 323 over 1404. We've got a 90% confidence interval. Our q hat is 1 minus p hat. And we ended up getting all these values. Plug it in, and that gives you your lower and upper bounds for the true proportion. So not so bad, pretty similar kind of idea, just a different formula. You just have to be able to pick out that stuff. And then also, we've got confidence intervals for variance and standard deviation. This one's a little different. We've got what are called chi-square charts. And it's really helpful to draw a picture for these as well. So for example, in this one, we had a 95% confidence interval. So that means each tail is 2.5% of the data. So we're looking for the area to the left of 0.025 for the left value and 0.975 from the right value, right? The 95% plus the 25%. Again, we use the degrees of freedom, same formula for degrees of freedom. And we line up the correct columns, and that gives us our values. Chi-squared left is the one on the left. Chi-squared right is the one on the right. And then we've got, this is our formula for the confidence interval for standard deviations of variance. N minus 1 times s squared over chi-squared right is the lower bound. N minus 1 times s squared over chi-squared left is the upper bound. So that's a little weird that the chi-squared right goes on the left and chi-squared left goes on the right. So just try to remember that. And that concludes Chapter 7. So Chapter 7, I've got 3 questions from Chapter 7 in the test. It's three questions from chapter 7, 3 from chapter 8, and 4 from chapter 10. And then we come to chapter 8. And what's chapter 8 about? Well, this is hypothesis testing. So hypothesis tests are a very, very rigid, formal way of talking about a statistical study. And there's two ways of doing it. There's the traditional method, which is the critical value method. That's the one that we learn. And the p-value method, but we didn't talk about the p-value method in this class, so I didn't include any questions like that on the test or in the work or anything like that. And so you've got to really remember the 5 steps for the traditional method. Number 1, you state the null hypothesis and the alternative hypothesis, aka the claim. The null hypothesis, you always use an equal sign. I think I wrote that here. Right, so in step 1, we're basically making some base assumption to revolve our study around. Like we have to have some starting assumption, some axiom, essentially. So that's why we use the equal sign for it. So we make this assumption, okay, this variable is equal to some value, and then we either try to prove or disprove it somehow with the alternative hypothesis. And the alternative hypothesis is either a less than, a greater than, or a not equal to, which I've put right here. And, you know, depending on the context of the question, of course, tells you if you want to use less than or greater than. And then if you're just looking for a difference, if you don't know if you're looking for greater than or less than, then you're just looking for not equal to. You're saying, oh, can I disprove this hypothesis, essentially? And that's essentially step 1. So, and remember, the null hypothesis is H sub 0, and the alternative hypothesis is H sub 1. And again, I put some good stuff here in the notes about when to use each symbol. And then step 2 is to find the critical values, which is essentially the boundary point for us deciding to reject or accept the null hypothesis. And so anything beyond that point is called a critical, or I'm sorry, anything beyond that point will cause us to reject, or I'm sorry, not accept the null hypothesis. It's called the critical range. And then the big, usually the big area, the rest is the what's called the non-critical range. And so if we use a less than, it's going to be a left-tailed test. If we've got a greater than, it's going to be a right-tailed test. And for the right tails, well, never mind. And for the not equal sign, that's a 2-tailed test. And so you've got to divvy up the remaining percentage equally amongst each tail, essentially. That's a left tail and a right tail. And then we go to step 3. And step 3 is to compute the test value. So that's the value given from the data in the sample. And then we'll use that data, we'll boil it down to a number, and we'll compare that number to the critical values and see if it falls in the critical range or not. And then we make the decision. If the test value is in the critical range, we reject H sub 0. If it's not, we do not reject. And then we summarize. So I've got 3 questions on the test, just like this, right? You've got to do all 5 steps. 1 for each section, essentially. 8.2, 8.3, and 8.4. Okay, and so same thing. When we know sigma, we've got to use this formula for z and use the z tables. We're essentially just formalizing everything we did in the last chapter. So we're not learning like new formulas. We're just learning our new the way of presenting the data, essentially. And so you know to do a hypothesis test whenever it's telling you to test the claim at some level of alpha. That's kind of the clue. Oh, I got to do a hypothesis test. And then you just, again, write out all the data that you can pick out from the context in the actual paragraph of the question. Well, I guess you do that when finding the test value. Never mind. It's best to go in order. So we just do step 1. And it says a researcher believes that the mean age of medical doctors in a large hospital system is older than the average age of doctors in the US, which is 46. Assume the population standard deviation is 4.2 years. A random sample of 30 doctors from the system is selected, and the mean age of the sample is 48.6. So we know the population standard div, so we know it's going to be this z-test and this z-formula. And it doesn't say like less than, it doesn't say greater than, anywhere like that. So this is going to be a not equal to on our null alternative hypothesis, I mean. Wait, does it say greater than anywhere? Sorry, guys. Oh, yeah, of course, sorry. In the beginning it says, a researcher believes that the mean age of medical doctors in a large hospital system is older than the average age of doctors in the US, which is 46. Sorry about that. Again, I'm sick, so sorry. My apologies. And so that's the claim, right? He thinks that the mean age is actually bigger than the average age in the US, actually mu, right? So that would be our null and alternative hypothesis. Remember, step 2 is to find the critical value, and that's based on our significance level, alpha. Again, you always want to draw a picture, and according to whether it's a left tail, right tail, or two-tailed test, that will help inform you on how to find that critical value. So alpha, essentially, that's the area of the tails. Since it's a one-tailed test, that's got to be 5%. The area to the left of that is 95% of the data. So we can look up our z-chart and get that it's 1.65. Then we find the test value, and we get that from all the data in the question and plugging it into the z formula. Get that right here. Then we compare the test value with the critical range. In this case, this one was in the critical range, so we will reject the null hypothesis. And then we summarize according to the context of the question. So that's always the 5 steps of a hypothesis test. Very formal, very rigid. Okay, and got other examples there. And then we've got, the same procedure for when sigma is unknown. And we use this formula for our t value. x bar minus mu over s divided by square root of n. And the df is still, of course, n minus 1. I don't know why the 1 went away. Let me put it back. And some more examples here, again, of course. And again, it says the sample standard div. So we know that we've got S that tells us to use this one, the t-test for the mean. And then we've also got a z-test for proportion. So we've got our formula here. And again, just bring in the formulas. That's fine. Have the formulas ready for the test. And here, remember, it's p hat minus p over pq, or I'm sorry, over square root pq divided by n. So, we're assuming that the population proportion is whatever they say it is. And then in this case, and so she thinks that 17% of young people ages 2 to 19 are obese. So we set that as our assumption, and then we try to disprove it, essentially. We don't know if it's higher, we don't know if it's less. So our alternative hypothesis in this case is p is not equal to 0.17. And it's a z-test, so we find the critical range by using the z chart. Then we calculate the test value, reject or not reject. So, they're all pretty much the same 5 steps. You just got to memorize the formulas and know when to use each formula based on the context of each question. And finally, chapter 10 on correlation and regression. So remember, this section is talking about trying to see if two variables are related, right? That's what correlation means, a correlation. Are they tied together in some way, essentially? And we're able to visualize this data in a scatter plot, x and y, where x is always the independent variable that we're trying to see has an influence on the dependent variable. So this particular example was using the independent variable of hours of study to try to predict their final grade percentage. So they were seeing if their hours of study had an effect or is related to a correlation with grade percentage. And there's also what's called a line of regression, which is basically a line going through the data, averaging it as best as it can, or as close to the data as possible. And that's called the line of regression. And we could also be asked to calculate that line of regression. And as you can see in these pictures that I've got here, the ones that are really clumped together, those do have some sort of linear relationship. They're close to each other when you graph them on x, y. The third graph, that would be something that has very, no relationship at all. There's no rhyme or reason. You can't really connect them in any way. If you drew a line through them somehow, most of them would be very far away from that line of regression. And we can measure, essentially, this relationship based on a value called the correlation coefficient. And it gives us a value between -1 and 1. And it's like a scale. The more negative the number is, the stronger the negative linear relationship is. So that means as x goes up, y goes down. Whereas the closer to 1 you are, that's a strong positive linear relationship. That means as x goes up, y goes up. And the closer the number is to 0 means the worse the relationship is, like that they're not related to each other at all, basically. And the formula for R is definitely not pretty. Uh, you know, no point memorizing it. Even in my in-person classes, I give them this formula on the test. It's just too much to memorize. So just make sure you know how to use it, that you can plug it in the calculator correctly, etc., etc. So remember, in order to do this, we've got two columns, x and y. And then we want to make extra columns for all the summations here. So I see a summation xy in the formula, so I know I need a column xy. We've already got a column for summation x and a column for summation y, so we don't need to add any new ones there. Then in the denominator, I see a summation x squared, so I know I'm going to need a column for x squared to figure out that sum. And I also see a sum of y squared, so we're going to need that column as well. So we should have x, y, xy, x squared, and y squared for our columns here to enable us to plug the information into the formula most efficiently. So that's what I did here in this example, right? It gives us the first two columns, the x and y. And then I came up with xy, x squared, and y squared as well, and then the sums underneath. So, definitely try to double check your calculations as best you can. There's a lot of room for error when doing this. You write one number wrong, the problem, it might, make the answer incorrect, of course. So just always double, triple check all your work when doing this. And I believe you could also pull up the Excel sheets on the test as well. And then again, of course, we just plug it all in. And get our value. And it turned out that this one had a high linear relationship. And another thing we could be asked is to calculate that line of regression that I was mentioning. And we've got a formula for that as well. I've got it right here. So you definitely want to bring this formula into the test as well. And it's a line. So the equation of a line is y equals mx plus b. And here we're going to say y equals ax plus b instead, where a is equal to that equation and b is equal, or expression, and b is equal to that expression, that other expression. And so we've already got all the data usually. Because first we see if there's a relationship or not, then we find the line of regression. So we should already have all those columns that we need. So at least that's nice that we don't have to come up with all those calculations again. And then we figure out what A is, figure out what B is, round them each to like 3 decimals or so. And then that will give us our line of regression, y equals ax plus b. And I had an example like that here. Another one here. Of course, plenty in the homework as well. And so again, there's 3 questions on chapter 7, 3 on chapter 8, 4 on chapter 10, for of course a total of 10 questions as usual. And that will be the last work for the semester. So I just wanted to say thank you all very much for working really hard in this class and doing really, really well. So many of you did really well, and I'm so happy with that, so proud of you all. Before you take the last test, of course, feel free to email me with any questions. If I have time, maybe I could schedule a couple minutes on WebEx or something if you have any really, really tough questions that you want to talk about. And I wish you the best of luck in studying. Again, I guess that's it. Thank you very much, guys. Always feel free to email me if you ever need anything, even in the future after the class is over, and I'd be always happy to help out my students. So thanks very much. Good luck on the test, and see you guys later.